a drive is included in such a way that a drive is inclined in such a way that rolling objects accelerate downward at 0.5 meters per second squared. This is the one we're talking about? All right. The driveway has seams every 2 meters apart. You watch a ball roll from somewhere above the first seam, and it takes 0.5 seconds to travel between seams. How far above the first seam did the ball begin its roll? All right. So this problem is got quite a bit of information in it. I think the hardest part about this problem is breaking down what information is important and pertinent and which information might be less useful or perhaps not what you think it is. So I find one of the things that will, I hope, help you is to start these problems by maybe sketching out a small picture. For those of you who think you can just kind of imagine in your head what's happening, that might work for you. But if you want success, draw a picture. It'll make a huge difference. So I'm going to draw a picture. So I have an inclined drive, and I know that somewhere on the drive there are seams, and the seams are 2 meters apart. The ball was released somewhere above the first seam. And I think when it was released, I think they're indicating it was released from rest. So when the ball was released, it started here with an initial velocity equal to 0. And then rolled down the ramp with an acceleration, and I'll make accelerations these kind of big, chunky arrows. An acceleration of, was it 0.5 meters per second squared? Can we agree that if the driveway stays inclined the same amount, that the acceleration will be 0.5 all the way down the driveway? All right. So what direction would you like to be positive for this problem? I think that's important. Yes, sir?
Down the hill.
Okay, so we're going to make down the ramp positive. If you're drawing a picture, and trust me when I say this will make a big difference, draw something like this. Put an arrow on the picture that indicates a direction that's positive. For the next unit we're going to do, pictures will be required for everything we do. This time they're kind of optional, but I probably bet that the people who can draw a picture of what's happening will do better than the ones who don't. So let's see if we know what's happening in this problem. And I'm going to start by kind of writing out my group of variables and seeing what information I can kind of glean from the problem. Remember, we have to be given 3 pieces of information in order for this to be of any use to us. So what information has been given here that I could write into this problem? Yes, ma'am? I could use the 0.5 seconds as time. Sure can. Yes, sir?
You have the acceleration.
I have the acceleration, positive 0.5 meters per second squared, because it points in the same direction as the arrow that I said was positive. Yes, sir?
Initial velocity is 0.
Now, here's why I have to be careful. The initial velocity is 0, but the 0.5 seconds, does that refer to the time when I release the ball from rest, or the time when it's traveling between the 2 markers on the driveway? We have to be careful here, because I think that some of the information has gotten mixed up. It says that I was releasing the object sometime above, or someplace above the seams, but the 0.5 refers to the time when the ball rolls between the seams. Everybody follow along? I mean, that's what I think the problem is telling me, which means I don't really know how long it took the ball to go from here to here. That time isn't known to me, but I know that it took the ball 0.5 seconds to go that distance. Do you understand why I'm kind of making this distinction? Now, we do know something about the distance between the seams. We know that it's 2 meters. So I could indicate that the ball traveled a positive 2 meters in that 0.5 seconds. But I don't think I know either one of these. Not for this. No, that's 3 pieces already. So I can use this information to tell me something. It's whether or not what it can tell me is going to be useful or not. But what is the problem actually about? What does it want me to find? Where's the question mark? Yes, sir.
How far it rolled above the first seam?
How far it rolled above the first seam. So I would like this displacement, right? During this displacement, the initial velocity is 0. During this displacement, I don't know the final velocity, but the acceleration has to be the same, positive 5 meters per second squared. And I don't know how long it takes to get there, but during this displacement, there are a few other things that I know. Now that's only 2 pieces of information, which isn't very much. I need 3. And I have 3 pieces here. Can anybody see a pathway that might solve this problem? Yes, sir?
We solve for the initial velocity or the final velocity of the first one, and you can put that into the second one.
So if I solved for this, I could use that here. All right. There is a way to do that. I'm not sure that's what you want to do. And let me explain why. This final velocity is how fast the ball is going here, right? That includes the 2 meters of displacement, right? So I don't know if that's what I want. But I do think there's something special about this one. Yes, sir?
I was gonna say the final velocity of the first part is gonna be the initial velocity of the second part.
I think that's what we can do. I think how fast the ball is rolling when it gets here appears in both sets of the problem. It's the initial velocity when it begins going between the 2 meters, but it has to be the final velocity for the time that it's sped up to get to the first seam. So I think you have to do 2 motion problems. I think you do this motion problem first, and then use this information here to do this motion problem second to get the displacement. Do you see why drawing a picture might help? If not, try it. I'm not sure you could have reasoned all that out in your head without separating it all out. I think drawing a picture makes a difference. This one is of higher level of difficulty. I'd call this a problem and not an exercise. So the first couple were exercises where the information was all about the same group of events, and you're merely plugging into the equation. I think a problem is a more useful opportunity to see what you are capable of doing. Okay? I don't need to actually do the work. Can you guys do the work? I think plugging it in is less interesting than actually figuring out what to do. So is there another homework question to which you'd like me to speak? In number 9, it appears that the first problem, which appears to be horizontal, there's a, for lack of a better thing, we'll say that's our rail cars. They're going to accelerate in this direction, but we don't know how much. But they're going to go from where they are to here. So this is the front of the rail car, this is the front of the rail car, and it travels the distance of the train, which is 12 meters. And when it is here, its velocity is 0, and when it's here, its velocity is 30. And is now traveling this way very fast. 30 meters per second, about 65 miles an hour. Interestingly enough, up until they opened up Test Track at Disney World, what was the fastest ride at Disney World?
Cheetah? Oh, Cheetah Hunt?
That's at Busch Gardens. But
Cheetah.
Cheetah Hunt's at Busch Gardens.
Oh, I thought you just said Busch
No,
Gardens.
Disney World.
Oh, oh.
Little known fact that the fastest ride at Disney World up until they opened up Test Track were the buses that took you between the parks. Rock and Roller Coaster, although has a great acceleration, doesn't go very fast. Most roller coasters don't go very fast. They They give you the perception of speed because they put you close to things that are moving by you. So they wrap you around poles and trees and stuff so that you feel like you're going fast. But most roller coasters don't go above 30, 40 miles an hour. So there are a few that are designed to go fast. And we have a few, but for most roller coasters, they don't need to be fast. They need to make you change direction quickly. That's what's exciting. The human body doesn't sense speed. That's why you could be in an airplane and not really know that you're going 600 miles an hour. But on a car, when you're going 60, it might seem like you're going super fast because the things are going by you quicker. That's why video games work. They can make you appear to be moving by showing you visual cues, but your body doesn't really know you're moving. Can't sense that. The only thing the body can sense is acceleration. It can sense that very well. That's why your body knows when it's accelerating, and then why some of you get motion sickness. So if I just look at this problem, it looks to me like I have enough information to figure out the acceleration. And the trick in this problem was realizing that they gave us a distance that the cars travel and accelerating, the length of the cars. Now, Rock and Roller Coaster does not really do this. But as an exercise go, it's not terrible. You're then asked to do the same thing with a bow and arrow. Where the arrow, is 0.75 meters long. So it's going to move 0.75 meters, starting with an initial velocity of 0 and a final velocity of, 80. And it's the same problem. So just different numbers. Don't drop your phone. You might want it. And there it is. Yeah, you don't want to be on the arrow. We don't shoot people with elastic. When we do, we use very long pieces of elastic and we shoot them straight up in the air to see them, on those funny videos where the people pass out. But generally, we don't accelerate rail cars or anything like that using elastic because it can be quite fatal. So, or springs. We don't use springs either. There's a lot of reasons why. We'll talk about those when we get closer to it, but that should be enough to get you started, I think. I want to talk to you about, let's talk about number 4, as it is a free fall problem. And here's where you might want to write a few things into your notes. Free fall questions or free fall problems are any problem where the object is accelerated by gravity. That's a free fall question. Any problem where the object is accelerated by gravity. Now, there are several things you should know about gravity that I'd like you to have in your notes. And like I said, this is actually the end of the kinematics notes. After this, we're going to study something else about kinematics, but the basic kinematics ends here. First, gravity accelerates all objects downwards with the same acceleration. Okay? All objects. So no matter how big, no matter how small, all objects are accelerated downwards with the same acceleration. And we call that acceleration the acceleration of gravity. A lowercase g is the symbol used for the acceleration of gravity. Now, why this is true is a much bigger conversation piece, and we're not going to have it today. The fact that it's true is not in dispute. You guys have dropped stuff or fallen yourselves, so you understand that things fall towards the earth. What you may not know is that there's something very specific about the way I should say this. The acceleration of gravity near the surface of the earth is 9.8 meters per second squared on all objects, regardless of their mass. It's a big sentence, and every part of it's important. The acceleration of gravity near the surface of the earth is 9.8 meters per second squared downwards, and is the same for all objects, regardless of their mass. Now that you've written all that down, add something to it. In our homework problems, we use 10, not 9.8. So if you know an object is accelerated by gravity, you're being given the acceleration. That's it. All objects that are accelerated by gravity will be 9.8 or 10. Now notice, I can't, or free fall in general, is anytime an object is being accelerated by gravity, we say that the object is in free fall. Again, anytime an object is being accelerated by gravity, we say that the object is in free fall. Now, I want to be really clear about this. The word fall there, probably distracting. If you throw a ball upwards into the air, the moment the ball leaves your hand, it's in free fall. So now, a lot of students get concerned by this. So let me address several factors related to this. So you throw a ball into the air, so, hand. Wow, that's terrible. But okay, art student, I am not. So the ball's in your hand, and you go to throw the ball upwards. Both your hand and the ball are accelerating upwards while you're pushing on the ball. Fair enough? The ball started from rest. Your hand provided an acceleration to the ball, and then you stopped moving your hand, but the ball kept going. Reasonable? The moment the ball is no longer touching your hand is when free fall begins. So there was an acceleration first that sped up the ball. We're not talking about that acceleration. Free fall begins the moment the ball is off of your hand. At that moment, gravity has taken over. And even though the ball isn't traveling downwards, we say the ball is in free fall because the only acceleration being experienced by the ball is gravity. Now, the ball goes up into the air, gravity stops the ball, gravity brings the ball back, it speeds up, and then there's this moment. The ball is traveling downwards now. You're about to catch the ball. Would you agree the ball is traveling with some downwards velocity just before your hand touches it? All right. So the free fall problem ends the moment the ball touches your hand or the moment it touches the ground. Because the moment it touches your hand or touches the ground, you're now not dealing with free fall. It's being accelerated by the ground or your hand. Are you going to stop the ball? Is that what your hand's going to do if you catch it? So if you're going to stop the ball, you are applying an acceleration to the ball now that is different than free fall. So a free fall problem only covers the moment the ball is left your hand and the moment just before the ball enters your hand or touches your hand. So a question like how fast is the ball traveling when it hits the ground? It's not asking about the fact that the ground might stop the ball. We know eventually the ball will come to rest. We're asking how fast it's traveling just as it contacts the ground, which means as it's still being accelerated by gravity. So don't get hung up on, well, if it hits the ground, it's going to stop. Well, yeah, so will your phone. The ground will eventually stop it. We're talking about how fast it was going just before it hit the ground. Does everyone understand that statement? Because they'll say how fast it's going when it hits the ground, and you might think, 0, he's trying to trick me. No, we're not trying to trick you. It's a speed at which it hits the ground. Now, the word free fall refers to the acceleration of gravity. And we use a lowercase g for the acceleration of gravity. We're going to see it a lot this year. It's a symbol for the acceleration of gravity. And the next sentence you should get in your notes verbatim, word for word. The acceleration for gravity, and then underline this next part, near the surface of the earth is 9.8 meters per second squared downward. For all objects, regardless of their mass. Every piece of that sentence is important. So I'll say it all again. The acceleration of gravity near the surface of the Earth is 9.8 meters per second squared downwards for all objects regardless of their mass. As an aside, in parentheses, put down that we'll use 10 meters per second squared for all problems. If you're asked to do a calculation, use 10. Don't use 9.8. The only time you'd ever have to use 9.8 is if you are told to do so by the problem. Otherwise, 10 is acceptable. The fact that it's 9.8 is just a fact of the Earth. Now, I got to handle all the pieces of that sentence, all the pieces, because there's several pieces there that you need to understand why they're in that sentence. I didn't say the acceleration of gravity is 9.8 meters per second squared. I didn't say that. I said a lot of other things. First, near the surface of the Earth. This is true only near the surface of the Earth. So if you go up into the mountains, it's not 9.8 anymore. It's less. The further away you are from the center of the Earth, the less this number is. So we say that this number is near the surface of the Earth, but it's not zero. Astronauts are not floating around in zero gravity. That's a misnomer. The acceleration of gravity out by where the space station is around 7, towards the surface of the Earth. They appear to be floating, but that is an appearance. That's because their spacecraft is falling towards the Earth. If I put you in an elevator and I cut the cable, you in the elevator will fall at the same rate. So inside the elevator, you'll appear to float for a short time. The only reason why the astronauts appear to float is because their spacecraft is crashing in the same way that the elevator is crashing. The good news is that the spacecraft is also moving sideways, so the Earth gets out of its way before it can crash. But that's really what's happening. It's like it's falling, and then it misses the edge there. But luckily for us, the Earth isn't flat, so it just keeps going around in a circle. But generally, that's why they look like they're floating. In fact, gravity is necessary for them to be in orbit. So there has to be an acceleration of gravity. Near the surface of the Earth, so this is not the same number on the moon. Right? On the moon, it's like 1.7 meters per second squared. On Mars, it's like 6 point something meters per second squared. Every planet will have a different acceleration of gravity near its surface because the planet is of different mass and different size. What controls this is complicated, but not so terribly complicated that we won't learn about it in a couple months. So keep in mind, this 9.8 meters per second squared is only near the surface of the Earth. And to be quite frank, lots of things affect this number. If you're standing over a natural water aquifer, this number will be different. If you're standing over granite, this number will be different. It's affected by the density of the ground beneath you. This was a way of actually finding oil deposits in the long ago past. By measuring gravity near different places around the Earth, you could figure out where the Earth was denser and where it was less dense. They would use that to find pockets of oil. Now, there's more to this. I said that this is the same for all objects regardless of their mass. That's pretty easy to see for things that are, heavy and are of a similar shape. So you got two forks here. I dropped them both. They'll probably hit my table at the same time. I don't think there's a surprise there. But not so between the mask and the fork. Don't be tricked. You're seeing something else happen to the mask that's not happening to the fork. What's happening to the mask? Yes, sir? Air resistance, right. So once we deal with gravity, eventually in the future, we're going to have to deal with air resistance. We can't evacuate the air from the room, and I don't have a chamber that I take the air out of so we can show this better, but there's plenty of videos on YouTube that'll show objects that all fall at the same rate regardless of their mass. It's always the feather and a pebble, and they'll drop it in an evacuated chamber and show that they both hit the ground at the same time. You need to convince yourself of that, find a video, but the truth is, for right now, for the time being, for the next couple of weeks, we will assume that air resistance isn't affecting our problems. But in real life, in real physics, air resistance will affect our problems. And we'll have to be careful about that. And we talked about that before your lab. So, all objects, regardless of mass, experience the same acceleration. That acceleration is 9.8 meters per second squared near the surface of the Earth. We will use 10 for any calculation that requires it. So, with that, let's do a quick, simple sample freefall question. All right? And I'm going to give you two different problems, although they are really the same question. Let's see if you can figure out what the answers are. Because I'm also providing you with the two tricks that are often given in free fall questions. They're not tricks, but people think they are tricks. Ready for question number one? Question number one, you throw a ball up in the air at a speed of 20 meters per second. How long till it comes back to your hand? Okay, example question number one. You throw a ball straight up into the air at 20 meters per second. How long till it comes back to your hand? This is a deceptively easy question, but students tend to have difficulty with it the first time they hear it. So you throw the ball upwards, 20 meters per second. I'm looking for how long it takes to come back to your hand. One thing that you will probably do better at when it comes to these problems, that will aid you and help you do better, is if you draw a quick little picture of what you think is happening. I guarantee you it will change the demeanor of your questions. If you think you can just reason it out in your head, you'll have a harder time. So maybe draw a picture or two. So I'm gonna pause for just 60 seconds to see if you can figure out the answer. This one is not too hard, but I'll pause. Now, I don't know how you decided to do it or if you got the right answer, but I want you to consider what the question was asking and a reasonable way you could have done it. First, when I am first given this information, I'm given an initial velocity, 20 meters per second. Since this is clearly dealing with when the ball left my hand, it's a free fall problem. So I'm going to recognize that the acceleration is 10 meters per second squared. That's only two pieces of information. So if you're trying to solve this problem, you're going to need to develop a third. When I think of this problem in my head, I think of the ball going up, stopping, and then coming back down. Do you think of it that way too? That's what I think of when I think of this problem. I'm going to make upwards positive. And from now on, when you draw a picture, if you draw an arrow with a positive sign, I'll be looking for it in your work to help direct me as to what you are calling positive in your problem. This also directs me to make my initial velocity positive, which I'll do explicitly, and my acceleration negative, which I'll also do explicitly, to make sure I understand that I've chosen a direction for positive. Now, choose a direction for positive. Don't have it chosen for you. In a problem like this, especially as we get into more complicated 2- and 3-dimensional problems, choose what you call positive. And be deliberate. Tell the person who's grading your test what direction you're calling positive. I still can't solve the problem until I know one more thing. What's one more thing we could bring to this problem? Yes, sir?
The final velocity,
What is it?
negative 20 meters per second.
Now, I don't know that there's a reason to believe that that's true unless you have some other knowledge that I don't have. Now, there's an argument you could make. Could you make the argument as to why the final velocity is negative 20?
So like if you throw it up at that velocity and it comes back to the same spot, it should be coming down at the negative velocity.
Well, that's not. I think there needs to be another sentence there, because you're just restating what you're telling me is true. You said, but why should it? I guess is the way I should answer. Is the way I should reply to you. Why should it come down at the same speed? Go. There it is. It has the same acceleration. I think that's probably the way to go. The acceleration that brought it to a stop at the very top is the same acceleration that brings it down. So there's every reason to believe it would come down at the same speed, since the acceleration was the same the whole time. That's very reasonable. See why I needed another sentence there? That's fine. So you could say negative 20. That's one way to do this. What's another way? There's about 3 different ways to do this problem. You were great. Let's find somebody else. Yes, ma'am.
The displacement would be 0.
Yeah, that's another way to do the problem. It came back to where it started. So you can make the displacement 0. That's fine. There's a third way to do this problem. Would you agree that going to the highest point is the halfway? You could make the final velocity 0 and find out how long that takes, and then double it. 3 different ways to do this problem. Doesn't matter to me which one you do. I am going to choose one of these ways on purpose, and I'm going to choose the one where we know that the displacement is 0. And I'm choosing it on purpose because I want you to see something else. So by choosing that one, I'm going to ignore that this is likely true as well. And the reason I'm doing that is because this is absolutely true. The other one, we had a reasonable argument to be true, but this one is absolutely true. So let's deal with this absolute. If that's true, then I'm looking for this, the time. So I'm going to use delta x equals 1/2 at squared plus vi times t. And that would be 0 equals 1/2 times -10 t squared plus 20 times t. Now, I know everybody in this room can solve this for t. However, it is very likely that the way you would solve it for t might violate a rule of math. And I want to make sure that you don't. First, simplify a little bit. 1/2 times -10, -5. Some of you would divide by t here. You shouldn't. Or maybe move the 5t to the other side and then divide by t. You shouldn't. Factor out the t. Remind yourself of your rules. This is a quadratic and therefore has 2 answers. It's likely you should find both answers. For this one, the answers might not make sense as to why there's 2, but I want them to. Remember, to get your 2 answers here, you have to set each one of these equal to 0. So I'll get t equal to 0, and minus 5t plus 20 equals 0. This one I can solve for t directly and get that t equals 4 seconds. There are 2 answers here, and the reason there are 2 answers is not, it's not obvious, but I want it to be obvious. When you have a quadratic, find both values for t. Even if you have to use the quadratic formula, find both values for t. And the reason is simple. We're asking math to tell us something. In this case, we asked math to tell us when the object was at the same location, at 0. So math has to provide us with the 2 times when this occurred. And this did occur twice, right? It occurred once when you first threw the ball upwards, and again 4 seconds later when the ball was coming downwards. There will always be a reason why 2 answers may exist. So it's incumbent upon you to not discard answers that are being given to you and to consider why you're getting 2 answers. In the future, this might be a more important detail. So whenever you're doing your math, please try to do the math as you were taught it. Don't use shortcuts. Don't divide by 0. That's what you would have been doing if you had divided it out by t. All right. The other trick, and there's not much of a trick left, I think you will catch this, is what if I asked instead, what was the maximum height attained by the object? Can you do that question too? Please try. What is the maximum height attained by the object? For those of you who are not sure where to start, consider that we're only asking about half of the object's motion this time. All right, I'm going to pause here because I don't want to spend a lot of time redoing a problem we've just done, because we really just did this problem. And so if you didn't know where to begin, let's get rid of all this and consider what parts of this could be reused. Can I reuse the displacement? Is the displacement 0? No. we're not talking about the situation in which the ball comes back to where it started. We're looking for this value. We want to know what the displacement is. How high was the ball actually able to travel before it came back down? Can we reuse the initial velocity being positive 20 meters per second? Yeah. Can we reuse the acceleration as negative 10 meters per second squared? Is this a free fall question? Yes, it is. Gravity is what's accelerating the object, so it is a free fall question. What do I need to add to this problem to be able to figure out the maximum height? The time? What would I put for the time? 2. Now that assumes I solved for the time previously and knew that the whole trip was 4. Is there something else I could do? Yes, ma'am. That's what I would prefer to do as an example. We know that the object reaches its maximum height when its velocity is 0. The fact that it was 2 seconds is because we threw the ball up at the same speed, so we expected half the trip. But I want you to know that maximums generally are when something is 0. So in this case, the maximum height is attained when the velocity is 0. So ignoring the time, I think we can put together a relationship that will tell us what the maximum height is. And I think there's a pretty straightforward one here. I would use VF squared minus VI squared equals 2A delta x. I think that's the way to go. 0 squared minus 20 squared equals 2 times negative 10 delta x. Be extremely careful when doing these problems. I'm very careful about signs. Now, some people think that when I square this side, that's going to make that value positive, but it won't. The negative sign is explicit in the function. The only time it would make something positive is if the initial velocity were already negative. So if I had said the initial velocity was negative 20, that would square it and make it positive. But this negative sign is explicit. So you may want to consider when you're dropping the velocity in there, you put a little parentheses around it to remind you of that. Or if you don't like that, use a different version of this equation. If you use this version, you won't make a minus sign mistake. I like this version better because it's related to something else, but this one will help you if you have issues with signs. Either way, 400 divided by 20. So 20. My answer is clearly positive. So pay attention to sign when you do this. Make sure you understand what a positive answer means. It means that it goes 20 meters upwards into the air. And that's when it reaches its maximum height.